Okay. And I said you had to use the chip model. With subtraction, how many sets do you have? With addition, you had more than one set. How many sets do you have with subtraction? Just one. So what's in my set? Or what color? Blue. All right, so I've got 4 blue ones. Now, what's it telling me to remove or take away? 3 what color? Blue. Is everybody with me? That's a positive 3. That's a minus, not a negative sign. They're not the same thing. So that means I'm going to remove. You're going to take that out. Now, is your answer what you take out? What's your answer? What's left? So you got to show me that you had 1 blue one left. So your answer is 1. Okay on that one? Now let's do one that's a little more trouble. All right, what if I said 4 minus 6? What kind of 4 is that, positive or negative? Not a trick question, what is it? Positive. What kind of 6 is that, positive or negative? Positive. All right, so that means that you have 4 blue ones. Now, what's it telling you to take away? 6 what color? Blue. What's your problem? You don't have 6 blue. So how are you going to fix your problem? What are you going to have to introduce in that problem? You can't just go adding some more blue ones. You can't just add numbers to your checking account because you like it. What can you add to a number without changing it? What can you add to 5 that won't change 5?
A 0.
A 0. What property says that you can add a 0 to a 5 and not change it? The identity property of addition. So what I better see so that's a 0 and that's a 0. And again, what property says that you haven't changed it? That's your identity property of what? Of addition. Right. Now, you're going to have to separate. It's going to mark on the right so it'll be better. Now think about what you did. Didn't you unstack those zeros? All right, so you still had your 4 blue ones. But when you unstack these, what did those zeros turn into? They were made up of a what? A positive 1 and a what? Negative 1. So these are what used to be the zeros. Okay? And the property that tells me that is that additive inverse property. Because that additive inverse property says that a negative 1 plus a positive 1 is indeed a 0. So it allows me to stack and get a 0 or to unbundle a 0 and get a negative 1 and a what? Positive 1. Now, can you physically remove 6 of your positives? You can, can't you? All right. So I can take and I can remove. I can take those out. You put out, remove, whatever. So you would have a set, and the only thing left in your set would be 2 what color? Red. So your answer is a negative 2. So if you can take things out, then take them out. If you cannot take them out, the only thing that you can add to the problem about changing it is a 0. And you can add as many zeros as you need. You can add extra ones, but if you add extra ones, you're going to make the answer a little harder to get because you have to simplify. Okay. So I needed 2 more blues, so that's why I added 2 zeros. I mean, I could have added 6 zeros, but that's just complicating the problem. So only add as many as you need. All right, so I'm sorry that we can't do it with manipulatives, but I can't have you closer to me than 6 feet for that length of time. So does everybody understand about how I want it drawn? Does that make sense? Now, most of the problems aren't going to be that way. Most of the problems are going to be you just work. All right, and I'll give you a work, part of your homework is going to be a worksheet where you have practice just doing. Okay, So if I give you one, and it just says work it. All right, here's the rules we have so far. All right, we know that a positive plus a positive is a what? Positive. And then we know that a negative plus a negative is a what? Negative. Now, what if you're adding one of these? So it can be a positive plus a negative, or it can be a negative plus a positive. Now, in that video that you had to watch, they wrote the rule down, didn't they? So that's where you subtract the smaller absolute value from the larger absolute value. All right. All right, so you subtract the smaller absolute value from the larger absolute value. And you take the sign of the number with the larger absolute value. Now, I know that takes a long time to say, but that's just what you have to do. Because if you say take the sign of a larger number, isn't a positive number always bigger than a negative number? So if you have something like 5 plus a negative 7, the signs are different. Well, what are you doing in your head? You're saying 7 minus what? 5. Because the absolute value of a negative 7 is 7, and the absolute value of a positive 5 is what? 5. And so you're taking the smaller absolute value from the bigger absolute value, and you just get what number? 2. All right, which one of these absolute values is bigger, 5 or 7? 7. What was the sign of the number that whose absolute value was 7? It was what? Negative. So your answer is not a positive 2, but a negative 2. Because you don't want, if you're comparing, we said on Zoom last time when y'all were on Zoom to make sure we're clear about this. How do you know when the number is bigger on the number line? How's a child supposed to know when the number gets bigger? How do you know what's bigger, 23 or 24? How do you know what's bigger, a -1 or a -3? Like, what's the correct answer right here? Because you're going to have these on your third test. Is it less than, equal to, or greater than? What's a -1 compared to a -3? Is it bigger or smaller? It's bigger. Why is it bigger?
It's closer to 0.
Because on the number line, it's further what? To the right. So the bigger number on the number line is always further to what? To the right. And when you're looking at a number line, -1 is further to the right than a -3. So a -1 is bigger than a -3. Okay? So now if you had -1 and a +3, then positive would be smaller than. Is everybody with me? If you had a -8 and a 1, -8 is also what? Smaller than 1. So if you just said take the sign of a larger number, 1's bigger than a what? -8. But a -8 plus 1 isn't a +7, it's a -7. Because the absolute value of that -8 is 8, and the absolute value of the 1 is a 1, and this 8's bigger than that 1. So you're comparing the absolute values, not the original numbers. Okay? So is everybody okay on adding? All right, so now on subtraction, what we put on the board last time on subtraction is you can rewrite it like an addition problem. Now, that's not what I want you to do when you're using the chips, though. Is everybody with me? I want the chips modeled as a subtraction. But your shortcut without the chips is you change it to an addition problem. Now, what happens to the first number? Like if you had a -3 minus 5, what would happen to the -3? Would it change or stay the same? All right, so that first term stays the same. All right, so -3 would stay a -3. What does that minus turn into? Okay, so change that minus to a plus. Now, what kind of 5 is that right there? Positive, so what does it turn into? A negative, so the second term turns into its opposite. Okay, so change the second term to its opposite. Then you've got an addition rule, and don't you have addition rules up here? So then you just follow the addition rules. Okay? So that's kind of adding and subtracting with integers. All right? So let's talk about multiplying and dividing with integers. Okay? Now, all right. What if you had a problem like this? All right, this one, so let's talk about multiplying. What if you have a positive times a positive? What's 2 times 3? It's just what? 6. 2 times 3 is 6 in second grade. 2 times 3 is 6 in college. So what's a positive times a positive going to get? A positive. Now I'm going to skip a negative times a negative for a second. All right, now, do you understand if somebody told you to model this with the chips? Isn't multiplication repeated addition? We talked about that with whole numbers. So I could either have 2 sets of 3 or I could have 3 sets of what? 2. So do we understand if I had 2 sets, what would be in each set? 3 what color? Blue. And so when you union them, when you get 6 blue ones. All right, so answer me this then. How do you think I would model this? What if I had a positive times a negative? In other words, what if I told you 2 times a negative 3? How would you do the chips? How would you model that with the chips? How many sets would I have? You tell me, how many sets? If 2 times 3 is 2 sets of 3, what's 2 times a negative 3? Still, how many sets? 2. What's in each set though? 3 what color? Red. All right. So you told me that 2 times 3 was 2 sets and I had 3 blue ones in each. So 2 times a negative 3 still means I have 2 sets, but now what's in each? 3 what? Red. Now, if multiplication is repeated addition, what am I going to do with these 2 sets? I'm going to what? Union them. So what ends up being in my set? How many? 6 what color? Red. Are we okay? Now, what if I had a negative 4 times 2? How could I illustrate that? Can I have a negative number of sets? That'd still be 2 sets. What's in each set? 4 what color? Red. If I had 3 times a negative 4, how many sets would I have? 3. What would be in each one? 4 what color? Red. So I'd have 12 red ones in all. Is everybody with me? So if you have a positive times a negative, or if you have a negative times a positive, what's the answer going to be all the time? Negative. Now, go back and look at your notes. People in class can look on the board. When you have a negative plus a positive, is it always negative? No, when you're adding a negative and a positive, sometimes it's negative, sometimes it's positive, sometimes it's 0. See, what's 2 plus a negative 2? What would that be? 0. All right? But when you have a negative and a positive and you're multiplying them, the answer is always what? Negative. Now, You're in college, so you probably know the answer to number 6, but you probably have no idea why. So we're gonna talk about that in a second. What's a negative times a negative? It's a positive. Now, what's a negative plus a negative? It's a negative. So you gotta get that straight. If you spend $2 and you spend $3 more, you have spent $5. Okay? So a negative plus a negative equaling a negative makes sense to most people. But for most people, a negative times a negative equaling a positive doesn't make so much sense. So let's make sure we're clear about why. Now, there are 2 ways to explain it to your students. One is using patterns and one is using properties. Now, using patterns is fine, but it's not approved. Using properties is better. All right, but some kids really like patterns and they make sense to them. Here, what do I mean by that? I mean this. Okay. 3 times a negative 3. Now that would be 3 sets. What would be in each one of those sets? 3 what color? Red. So they could use the chips to figure out what's this answer going to be. What kind of 9? Negative 9. This would be 2 sets. What's in each set? 3 what color? Red. And so when they union them, they get a negative what? 6. This is just 1 set. What's in your 1 set? 3 what color? Red. So that's just a negative what? 3. You know what 0 times any number is. What's 0 times any number? What property? I can ask you this on your test Thursday. What property says that 0 times any number is 0? Your 0 property of multiplication. Now look at your pattern. We did patterns back in chapter 1, remember? So negative 9, negative 3, negative 6, negative 3, 0. What's happening every time you get to the next number? You going up or down? Up. By how many?
3.
So what's that going to have to be? 3. For that pattern to continue, aren't you adding 3 every time to get to the next number? Now, that works for a lot of students, but I'll be honest with you, it would not have worked for me as a kid. I'm that kid. Because my take back to you would be, well, I thought I found shortcuts a lot of times and then they didn't work later. So let's show you, this isn't a proof, but it's almost a proof. The high school students have to be able to prove it. Do we agree that 2 times 0 is 0? All right, what about negative 2 times 0? Is that still 0? So if I ask you on your test, why is a number times 0 equal to 0 on Thursday, what are you going to tell me, remind me? 0 property of multiplication. Now, give me 2 numbers that I can add together and get a 0. Just don't use 1 or 0. Let's use a different pair just to kind of make sure. What are 2 numbers I can add together and get 0?
2 and negative 2.
2. Well, so we got 2 here. Pick me another pair.
3 and negative
3 and negative 3. Now, what property says that 0 is the same thing as 3 plus a negative 3? Additive inverse property. So I can justify what I just did by a property. Now, what property did I just use to get from here to here? Because I might ask you that on your test Thursday. What property says that this number times this parenthesis is this thing? Distributive property of multiplication over addition. Now, they've already gotten this answer with the chips. If you have 3 sets and in every set you have 2 red ones, what's this answer going to be? Negative 6. I don't know what that answer is, but I know when I add these 2 numbers, I have to get what? 0. Well, there's only one number that I can put in there and make it true. What do you add to a negative 6 to get 0? Positive 6. What property says that a negative 6 plus a positive 6 is 0? The additive what? Inverse property. When you read the additive inverse property, it says this, that every number in its unique additive inverse. If something's unique, how many of them are there? Just what? One. So it guarantees there's only one number that you can add to a -6 that will give you 0. And it's got to be a +6. So a negative times a negative must be a what? Positive. We okay? Now, so let's make sure we're clear. We've got that a positive times a positive is a positive. And then I'm going to write this differently. A negative times a negative is also a what? Positive. And then when you have a positive times a negative, or when you have a negative times a positive, that answer is always what? Negative. Now, luckily, your division rules are the same as these. And by that, I mean this. What's a positive divided by a positive going to get you? A positive. What's a negative divided by a negative going to get you? If these rules match, a positive. And if you have a positive divided by a negative, or if you have a negative divided by a positive, that answer is going to always be what? Negative. So there are your rules that you have to learn before your third test. Now, do you remember that I told you you can't hold too many facts in short-term memory? All right, I want you to look at these 6 rules. There's a way to change those 6 rules to 2 rules. How could I rewrite those 6 rules and turn them into just 2 rules? Look at these 2 and these 2. What do you notice? They all equal positive numbers, right? So how can I phrase it so a kid would know when you're multiplying and dividing, how do you know when the answer is positive?
If the numbers that you're multiplying or dividing are the same, positive or negative.
That's right. That's exactly right. When you're multiplying or dividing, if your numbers have the same sign, what's the answer? Positive. What if you're multiplying and dividing and your answers have different signs? So that's a way. Now, so think about it. One of your jobs as the teacher is not just to go by the book, but to improve it. Okay? So if you've got a student who has a hard time memorizing a bunch of different things, you have to figure out a way to help that student rewrite rules. So instead of learning 6 rules, I can change them to 2 rules. When I'm multiplying or dividing, when the signs of the number are the same, the answer is positive. When I'm multiplying or dividing and the signs of the answers are different, the answer is what? Negative. So the fewer the rules they have to memorize, sometimes the easier that it is. Now, I want to make sure we're clear about something. On your third test, you're going to have problems that have several parts to it. So on your worksheet, you're going to have some that are like -4, -7, but you're going to have some that are more like this. So they may be strung out all over the place. Okay? So we've got to follow our order of operations. So what's the first thing we always look for in order of operations? Parentheses. All right, do I have any in this one? No, if I did, I would do it. All right, what's the next thing you look for? All right, do you have any exponents? You do, don't you? All right, well, you got to go to the first one you have. And if you do one thing per line, you're less likely to make a careless error. So eventually I've got to do this one first. Now, that's going to be 3, what? Is it going to be -4 or +4? Be very careful. What does this 2 go with? Just the what? With the 2, not with the minus. Is everybody with me? An exponent goes with what immediately precedes it. So do you understand that would be 3 minus what? 4. So all I'm doing is this 2 squared. And everything else just gets copied. Then you start back over on the left. Are there any more exponents to do? Then I gotta go do that. Everything else just gets copied. And again, this 2 only goes with that 8. Now, if it was like this, then the 2 would go with the 8 and the what? The negative. So there's a difference between these 2 things. An exponent goes with what immediately precedes it. This would be minus 64 or a negative 64. This is going to be a positive what? 64. So you got to be careful. All right, what is 8 squared? 64. Are there any more exponents? No. What's the next thing you look for? Multiplication, or do you always multiply before you divide? No, it's whoever gets in line first. So when I'm looking left to right, which one comes first, the multiplication or the division? The multiplication. So I've got 3 minus. Now what is 4 times 4? 16. Then the rest of it just gets copied. All right, do you see any more? Start back to the left every time. Do you see any more multiplication or division? Yeah, what do you see? 64 divided by what? 2. Everything else gets copied. All right, so what is this 64 divided by 2? Isn't that 32? And I've still got this plus 1 what? Minus 3. Now start back on the left. Do you see any more multiplication or division? So what's the last thing you do? Adding and subtracting. Okay? Now for some people, they're going to need to rewrite this. Can they rewrite it as addition problem if they want to? Yeah, I'm not going to make you, but you can. Is everybody with me? So what's 3 minus 16 going to give me? Do you understand it's a negative 13? Because if you got 3 minus 16, isn't that the same thing as 3 plus a what? Negative 16. All right. Then I've still got my minus 32 plus 1 minus 3. Now again, I'm always starting back on the left. Don't just keep going. All right. The next thing I see is I've got negative 13 minus 32. Now again, if you need to go to the side and put negative 13 plus a what? Negative 32, you're welcome to do that. What is a negative 13 minus 32 more? The sign's the same. So don't I add their absolute values? So what am I going to get? A negative what? Negative 40 what? 5? All right, what's a negative 45 plus 1 going to give me? And they're going to be a negative 44. And then I'm subtracting what? 3. So what's my final answer going to be? A negative what? Everybody okay? All right, so you'll have some of those to kind of play with. So make sure that you're good on your integers. Now, the video that you watched talked about the number line model. So you got the chip model and the number line model. Now, for me, the number line model is pretty good when you're adding and subtracting. It's not so good to me when you're multiplying and dividing. Okay, but let's make sure we're clear about something. We've already talked about these, but we're doing whole numbers. If you're doing number line model, what's the first number tell you where to start? And so we always started with 0. So So we would start with 4. When it was plus, which way did you go? To the right. And then the second number tells you how many units to move. What was the difference when you were doing subtraction? You go to the left. Now, what you don't want to do is contradict yourself later. And what you don't want to do is make the teacher's job above you harder. So if I am the first grade teacher or the kindergarten teacher, that's what I'm going to tell them. The first number is where you start. If it's plus, if it's addition, you turn which way? To the right. If it's minus, what are you going to turn and go? To the what? To the left. And the second number tells you how many units. So what's going to happen when they get to 5th grade or 6th grade and they see these kind of problems? Well, if it were me, I don't want to contradict the first grade teacher. So just like the first grade teacher, what's the first number going to tell you where to what? Start. When it's addition, what should the child do? Go to the right. If it's subtraction, the child's going to go what? To the left. But when you hit that sign, now what does that sign mean? It means negative, right? What's another word for negative though? Opposite. So if you hit an opposite, you've got to turn and go in the what? Opposite direction. So that kid starts out just like before on a -4. All right, so they start right there. And usually I have them physically stand on a number line made out of like painter's tape so I don't destroy the floor. Okay, and so a kid goes to the front of the room and stands on the floor. And when they see plus, they turn to go which way? To the right. But then you hit that opposite. So what does that mean? Now I've got to do what? Turn and go in what? Opposite direction. And this second number still tells me to move how many units? 2. So they're literally going to move 2 units to the left and they're going to stop right there. So their answer is a what? A 2. Similarly, if they had 4 minus a -2, they'd be standing on 4. When it says minus, which way are they going to turn? Which way? To the left. But then when they hit the negative, what do they got to do? They got to turn and go in the opposite direction, 2 spaces, and then they're going to end up in 6. So that way, the thing that you told them in 1st grade is still true in 5th grade. Addition, you go right. Subtraction, you go left. Okay? In the video, she would say go toward the negative numbers. I find that confuses them a bit. Because they've already learned to go plus, you go to the right, minus, you go to the left. Just that negative means turn and go in the opposite direction. Okay. Now, that kind of helps us finish up that chapter 5 on integers. Okay, like I said, part of your homework will be to have a worksheet. Now, what we're going to start about now are something called rational numbers. All right, rational numbers. So we're starting chapter 6. We're starting chapter 6 on rational numbers. Now, here's the definition of a rational number. A rational number is a number that can be written as an integer divided by another integer. As long as the bottom integer is not 0. All right, you write that in your notes, and I'm going to rewrite it the way the book writes it. Okay. All right, so it's a rational number, it's a number that can be written as an integer over or divided by another integer, as long as the bottom integer is not what? 0. Now, The way that a lot of math books write it, they write the same thing, it just looks kind of symbolic. Because like I said, mathematicians tend to like symbols more than words sometimes. So let me kind of show you what I mean. They would write it like this. It's a number that can be written as A divided by B, where A and B are integers, and B is not equal to 0. You see that that says exactly the same thing I said in words a minute ago. Now, what's the very first set of numbers we've said that children learn? What's the first thing kids learn to do with numbers? They learn to count. So we call those natural numbers. 1, 2, 3, and it keeps going. All right, counting numbers are natural numbers. Then we said when they get to kindergarten, they find out there's a number that stands for nothing. Okay, what number stands for nothing? 0. So when you put 0 with these numbers, what set do you end up with now? Whole numbers. All right, so do we understand that the natural numbers are a subset of the whole numbers? Now, whole numbers and natural numbers are both subsets of integers. 2 is a whole number, a natural number, and an integer. 1 is an integer. What's in this little outer ring that's not a whole number though? The negatives, the opposites of these whole numbers. So you also have like a -1 and a -2 and a -3. Is everybody with me? So now our set is growing again, and this is where we are now. These are rational numbers. So let's make sure we're clear about something. So example. Is that number 3/4, is that a rational number? Yeah, because it's an integer divided by another what? Integer. Is a -1/2 a rational number? Yes. Why? How can you make a -1/2 a rational number? What integer can be on top of what other integer? Because the whole fraction is negative, but I have to have an integer over another integer, and so I can have a sign in front of it. Do you understand that a -1/2 is either a -1 divided by a +2, or it's a what? +1 divided by a. Do we understand that a -1/2 is not a -1 divided by a -2? How do I know it can't be that? What rule do we just learn about a negative divided by a negative? It's a positive. So that negative can either go with this top number, we'll call it the numerator in a minute, or this bottom number that we're going to call the denominator. But it doesn't go with what? With both. But see, a -1 is an integer, and a +1 is an integer. And a +2 and a -2, they're both integers. Now, is a 3 a rational number? Isn't it inside this big red circle? Okay, but what doesn't say is written, it says what? Can be written. That's why it says can be, not is. How can you write 3 as an integer over another integer? You can put 3 over what? 1. Is 0 a rational number? Yeah. How can you make 0 an integer over another integer? 0 over what? 1. What about a -10? Is that another rational number? Yeah, because I can make it a -10 over what? 1. So do you understand that all natural numbers, whole numbers, and integers are also what? Rational numbers. Now, We're jumping ahead, but this makes more sense to people when I teach it here. All right, we're gonna get to decimal numbers after we get to fractions, which is a little bit backwards from sometimes the way it's taught. Okay, but this is a pet peeve of mine, so we need to start learning it early. We're gonna read decimal numbers correctly. Because if we do, life is great. If we don't, life is terrible. All right, so let's learn to read decimal numbers. We're kind of jumping ahead a little bit. Okay, when you got decimal numbers, you read the number to the left of the decimal the way that you normally would. What number is that? 4. What number is that? 12. What number is that? 0. The decimal is read as the word and, A-N-D. Then you read the number to the right of the decimal the way that you normally would. What's this number?
35.
Not this what? 35. What's that number? 3. We don't say, what is that number? That's just a strange way of writing what? 41. So you read the number to the left the way you normally would. You read the decimal as what word? And then you read the right number the way you normally would. It's just the last word out of your mouth is the place value of the last digit. Now, this is kind of jumping ahead, but what place is that 3 in? What number's to the right? What place is to the right of the decimal? What place is that 0 in? Let's start there. Is that my tens place? What place is that 0 in? Surely we know. What place is this 2 in? The ones place. What place is that 1 in? The tens place. What place is that 4 in? The ones place. What place is that 0 in? Ones place. So what's the first column? What's the first digit to the right of the decimal column? What place is that? It's the tenths column. What's the second place to the right column? The hundredths, THS. What's the third one to the right column? The thousands, THS. Is everybody with me? So do you understand, if you're trying to read this number right here, how would you read that number? 12. What's that read as? And read that number. 35. What place is that? Hundreds. Well, all you have to do is write down what you said when you want to go between fractions and decimals. What did you just say? You said 12 and what? 35 what? Hundreds. Now, normally we don't say 0 and. Everybody with me? When there's a 0 in the front, normally we just say, what is this number? It's 3 what? Tenths. Isn't that an integer over another integer? So when we get to decimal numbers, you understand decimal numbers are also going to be what? Rational numbers. Because I can change this mixed number when we get to fractions a little bit more later. We're going to be able to change that mixed number in a minute into a fraction. So again, I'm going to have an integer over another what? Integer. That's why if you're the first grade teacher, I do not want you to do this. All right, do you see that number that's boxed up there? That is not 105. That's just 105. Don't let them say and, because that and's reserved for the what? For the decimal. Because when they get this later, you don't want them to say 105 and 1/10. You see what I'm saying? They'll get lost. So if you teach them to read things correctly all the way up, life's going to be super, super easy. So rational numbers are going to be all of our fractions and all of our decimals. Everybody with me? Okay, but we're going to be keying in on fractions for right now. Okay? So let's make sure we're clear about something. This top number is called my numerator. And that's what I'm not going to call it top number. We're going to call it numerator. All right, this bottom number, we're not gonna say bottom number, we're gonna call it by its proper name, denominator. Mathematical practice number 6 in Common Core says attend to precision. And that doesn't just mean I can measure to the nearest 1/10 of an inch rather than the nearest 1/2 of an inch. That also means precision in language. So if we start calling things by their proper name, life ends up being great. All right, now, I want you to do this on your paper. All right, I want you to draw a circle. Just, I'm not going to look at it, just draw a small circle, and I want you to shade 1/3 of it. So just draw a circle and shade 1/3 of it. Now, if I walk into a 4th grade classroom and I want to know if the kids really understand something about a fraction, that's the first thing I would ask them to do. Draw me a circle and shade 1/3 of it. Because when I do that, here's what I get a lot. Is that correct? And the answer is no. Why not? What does 1/3 mean? Does it mean 1 out of 3 pieces? Not exactly. It means 1 out of 3 equally sized pieces. So I need you to make sure you tell them that all the time. See, these 3 pieces are not the same size. So that's not 1/3 of the circle. Now, if I do like this, now my pieces are the same size, and it really is what? 1/3 of the circle. So do you understand that when you got a fraction, this denominator tells you how many equally sized pieces make a whole? And this numerator tells you your number of pieces. So 1/3 does mean 1 piece out of 3 equally sized what? Pieces. And how many equally sized pieces make a whole? 3. So the first thing I expect a student to be able to tell me is a fraction less than a whole, exactly a whole, or more than a whole? So if I've got this number, or this number, or this number, they should be able to tell me whether they have less than a whole, exactly a whole, or more than a whole. All right, what is 2/5? Less than 1, exactly 1, or more than 1? Less than 1 takes 5 equally sized pieces to make a whole, and you only have how many? 2. You got less than a whole. Here, how many equal sized pieces make a whole? 6. How many do you have? So what do you have? You have 1. You have a whole. All right, here, how many equal sized pieces make a whole? 3. How many pieces you got? You have more than a whole? Yeah, as a matter of fact, you got more than 1. You got more than 2 holes, don't you? Here, do they have more than a whole, exactly a whole, or less than a whole? Less. It takes 9 equal sized pieces. You've only got what? Are you close? Yeah, you're close to 1, but you're not there yet. All right, what about 10/15? Is that exactly a whole, less than a whole, or more than a whole? Less. It's less than 1. What about this? That's exactly 1. That's exactly 1 whole. Okay? So one of the things I expect kids to do is that. Now let's talk about this. 2 different things. We're going to talk about changing from fractions to mixed numbers and mixed numbers back to fractions for a second. For me to do that, I need to talk about a proper fraction versus an improper fraction. A proper fraction has the numerator less than the denominator. So that would be things like 1/2 and 10/15 and 11/17. That top number is smaller than that bottom number. That's what it needs to be proper. What does the prefix IM mean in math? If you were improper, what does that mean? You're not proper. So that means the numerator is not less than the denominator. So what would it have to be then? So what would it mean? The numerator would have to be what? If it's not less than the denominator, it's either what? Greater than or equal to the denominator. So that will be problems like 8/3 or 17/11 instead of 11/17 or 3/3. Okay. So if you have an improper fraction, we change those to what are called mixed numbers. Now, when something's mixed, don't you have different things there? Okay. Let's talk about what a mixed number is. A mixed number is the sum put it this way, of an integer and a fraction. Now, they're not dealing with negative numbers probably when they first start, so you might even put whole numbers. Now, this goes back to this idea of bundling and unbundling that we've been talking about. See, if I've done my job as the kindergarten teacher and the first grade teacher, then I'm going to make this teacher's life a whole lot easier. So, for instance, do we understand if I want to do 8/3? Do we agree that 8/3 is improper? All right, how many pieces do you have? You have how many pieces? You have 8 pieces. Can you make a bundle and make a whole? Yeah. How many is it going to take to do that? How many pieces? So if you take out 3 pieces, won't that make a whole? In other words, it's a what? Bundle. You're going to bundle things into wholes. Now, when you do that, how many pieces will be left? Will there be 5 pieces? Can you make another bundle? Can you make another whole? Yeah. How many pieces you got to use to do that? 3. How do you know that? Because that's what the denominator tells you. So again, that's going to be a whole, what they've been calling a what? A bundle. Now, how many is that going to leave you? How many pieces? 2. Can you make another bundle or another whole? No. So notice what you did. You had a whole, plus you had another what? Whole, plus you had 2 what? Pieces left over. We agree? Do we understand that a whole is a 1? And I have another what? 1. And then I don't have enough for another whole. Now, how many equally sized pieces make a whole in this number? 3. How many pieces do you have? 2. So what is a 1 plus a 1 plus a 2/3? We write that as 2 and what? 2/3. But I want you to notice something. There's an understood symbol between the 2 and the 2/3. Do you understand that 2 and 2/3 means 2 plus what? 2/3. There's an understood addition symbol between those 2 things. 2 wholes plus part of a whole. Now, that's a little confusing when they get to algebra. Because when they get to algebra and they have 5x, there's not a symbol between those. What's understood to be there? Is it addition? It's what? Multiplication. So sometimes when a symbol's missing, it's multiplication. Sometimes when the symbol's missing, it's what? It's addition. So it's going to be real important when you're the elementary teacher that you make sure they understand that 2 and 2/3 means 2 what? Plus 2/3. Because if we start adding and subtracting, that's going to be crucial for them to understand. Now, look at 17/11. All right, 17/11. We said that's improper, so it's at least a whole or more. Now, what is this 3/3? What's 3 divided by 3? It's 1, isn't it? What about this? What's 6 divided by 3? What's that going to simplify into? 2. Because again, if you have 6 pieces and you take out 3 for a whole, that's going to leave you 3 pieces. When you take out 3 for another whole, that's going to leave you what? No pieces. So a whole plus a whole is how many wholes? 2. I just have 2 wholes. We okay? Now, 11/17. What mixed number is that going to be? 1. Because how many pieces did you just use up? 11. So how many pieces are going to be left? 6. So 1 and what? 6/11. Now, sometimes we would do this over and over. Now, next week, we're going to play with manipulatives, pattern blocks. Okay? So I'm jumping a little bit ahead for homework purposes, but after we play with the pattern blocks, I would make them literally do this with small numbers. Because I want them to see if they have 13/5, how many equal sized pieces make a whole? How many? 5. How many did you got? You got how many pieces? 13. So see, they've got 13 pieces. They take out how many? 5 pieces, because that makes a what? A whole. That's going to leave them what? 8 pieces. Can they take out another whole? Yeah, how many they got to use? 5 pieces. That leaves them what? 3 pieces. Can they make another whole? No, so they've got a what? They've got a whole, plus they've got another what? Whole, plus they've got 3 what? Pieces. You might put. So they've got a whole, plus a whole, plus now they've got 3 pieces. How many equal sized pieces make a whole? 5. So they've got 2 and what? 3/5. Now, we don't want to keep doing that when we end up with problems like this. 61/3. That'd be a lot of subtracting. So after we've done this over and over and over and over, and I'm convinced they understand it, aren't you doing repeated subtraction? What is repeated subtraction the same thing as? Division. So there's a shortcut. But I would never show them the shortcut. They would figure it out for themselves, with me would help them a little bit. So do you understand, if you want to change an improper fraction to a whole number or a mixed number, what's step 1 going to be? Would not be subtracting 3's a bunch of times. And what did you tell me repeated subtraction was the same thing as? Division. So what am I really going to do with that numerator and that denominator? I'm going to divide that numerator by that denominator. See, 8/3. 8's going to get divided by 3. How many 3's can I pull out of 8? 2. Did we get 2 wholes a minute ago? Wouldn't that use up 6 pieces when I did that? What would be left? 2. Is everybody with me? So what are you going to do with this remainder? Isn't that how many pieces you have left over? Would you have to put it over?
3.
Why the 3? Because that's how many equal sized pieces make up whole. So do we understand? Then you're gonna, so the number on top of the division problem is the whole number. Okay, or the integer when you get to negative numbers. And then you're going to put the remainder over the divisor for the fraction. we understand if I had something like 27 halves, I'm going to take that numerator and divide by my denominator. How many 2's can I pull out of 2? 1. That's going to leave me nothing. My next number comes down. How many 2's can I pull out of 7? 3. That's going to leave me 6. How many pieces are left over? 1. So do we understand that the 13, the number on top is my whole number? Do I put 2 over 1 or 1 over 2? Do you see if they've subtracted a bunch of times, they won't get confused? So I get 13 and what? 1/2. That's what 27 halves is. You can pull out 2 13 times and have 1 piece left over. Are we okay? Now let's go the other way. What if we wanted to change mixed numbers to improper fractions? All right, what if I had this? 3 and 1/4. Now, how many wholes do I have? 3. So do we understand that I've got a whole plus a whole plus another whole plus part of a whole? Right? How many pieces is this whole going to be unbundled into? How many equally sized pieces make a whole in this problem? 4. So when I take this whole, it's going to unbundle into how many pieces? 4 pieces, doesn't it? What's that whole going to unbundle into how many pieces? 4. And again, that's going to unbundle into how many pieces? 4 pieces. All right, this part of a whole has how many pieces? 1. How many pieces do you have in all then? Don't you have 13 pieces? How many equal sized pieces make a whole in this problem? Are we okay? What if I had 2 3/5? How many holes do you have? 2. So do we understand that we have a whole plus part of a whole? Are we okay? Now in this problem, how many equal sized pieces make a whole? 5. So this whole will get unbundled into 5 pieces. What's that whole going to get unbundled into? 5 pieces. Now, do you see your part of a whole? How many pieces do you have on your part of a whole? You have 3 pieces. Then how many pieces do you have in all? 13. Now, is it always going to be 13? I got 13 over there and 13 over here. Is that just a coincidence? It's a coincidence. I've got 13 pieces. How many equal sized pieces make a whole? Does that make sense to everybody? Now, again, I don't want them to, now they would do this for days. Everybody with me? I mean forever, but you're not in the 3rd grade. There is a shortcut. If I had 4 2/5, what is repeated addition the same thing as? Multiplication. So do you understand how many equal sized pieces make a whole? How many holes do you have? 4. So how many pieces would that be? 20. Then, don't you have some other pieces? What would you have to do with that 20 and that 2? You'd have to add them. Wouldn't that give you your new numerator? So do we understand your shortcut here? You would multiply the whole number and the denominator. But do we understand why now you do that? Are we okay? Then you're going to add the numerator to that product. That answer is your new numerator. and you keep the same denominator. Now, there's nothing magical about shortcuts. If the shortcut bothers you, don't use it. Do it like that. You only get points for being right, not fast. So, do we understand then if I gave you this? 5 3/7. How many equal sized pieces make a hole in this block? 7. How many holes do you have? So if you've got 5 holes, each of those has 7 pieces. How many pieces is that? 35. Then you have to add your other what? 3 pieces. So now I'm up to what? 38. That becomes my new numerator. What's my denominator going to stay? Where's your homework going to be? Now, what's your homework for Thursday? To study. Is everybody with me? But I'm going to go ahead and post the homework for next Tuesday. Okay, in other words, I'm going to go ahead and post Thursday's homework. And it's going to be on multiplying and dividing integers and on this part of the fraction. Okay?